All right, let's take something we see every single day, plastic, and put it in a situation that is, well, anything but ordinary. What actually happens when you subject this everyday material to forces so extreme they could literally tear steel apart? The answer is probably not what you think.
You know, plastic is everywhere. Our water bottles, our cars, you name it. We think of it as flexible, maybe a little brittle. But what happens if you hit it with a shockwave that's moving faster than the speed of sound? Does it just shatter into a million pieces? Does it melt? The reality, it turns out, is way, way stranger.
You see, under the incredible stress of a massive shockwave, polymers don't just have one simple reaction. It's almost like they have a split personality. Depending on just how intense that shock is, they behave in two fundamentally different ways, revealing this hidden complexity we just never get to see.
So that brings us to our first deep dive here. A tale of two shocks. We're going to explore the huge difference between a relatively weak impact and a truly strong one.
And the difference is, well, it's night and day. Under a weak shock, those long polymer chains, they just kind of shift around and reorganize. Sure, the material's properties change a bit, but it's still fundamentally the same stuff. But with a strong shock, at those extreme pressures, everything changes. Chemical bonds are violently torn apart, and the material transforms into something completely new, completely losing its original identity.
That whole weak shock behavior can be explained by this key concept, a phase transition. And that simply means the material changes its internal structure. Just think of water turning into ice. It's still H2O, right? But the molecules are just arranged differently. Well, that's pretty much what's happening to some of these polymers under pressure.
Okay, let's take Teflon, for instance. Yeah, the stuff in non-stick pans. When you hit it with a relatively weak shockwave, it doesn't just disintegrate. Instead, its crystalline structure just reorganizes itself into a new configuration. It's still Teflon, just packed together in a different way.
And scientists have actually measured this precisely, which is just incredible. This phase transition in Teflon happens at around half a gigapascal. Now, to put that into perspective, that's like balancing the entire weight of a small car on the tip of your finger. It's a massive amount of pressure. But in the wild world of shock physics, it's really just the beginning.
So, that's the first personality, the shapeshifter. But what happens when we go way beyond that sort of gentle rearrangement? What happens when the force becomes truly, overwhelmingly powerful? This is where the story gets really good.
So now we're entering the realm of the strong shock, a phenomenon that researchers call the Great Carbon Convergence. And it's a transformation so shocking, it basically defies everything we think we know about how materials are supposed to behave.
All right, here's a thought experiment for you. What if you take three completely different plastics, say soft rubber, hard epoxy, and slippery Teflon, and you hit all of them with the same unimaginably powerful shockwave? You'd probably expect them to fail in their own unique ways, wouldn't you?
While the science says something else entirely. The research is just astonishing. It says that diverse polymers homogenize. They literally become the same, converging into structures that behave similarly.
Let's just put that in plain English. You hit them hard enough, and it doesn't matter if you started with rubber or epoxy or whatever, the shock wave is so violent that it just rips the complex molecules apart, strips away the other atoms, and crushes what's left into this generic, super-dense solid that's made mostly of carbon. They all become one.
And the crucial point here is the threshold. This incredible transformation really kicks off for many polymers at around 25 gigapascals. Remember that pressure that changed Teflon? This is 50 times greater. At this point, the individual identity of the plastic is just gone, obliterated.
So, okay, polymers turning into carbon under extreme pressure is fascinating, for sure, but why does it matter? Well, this brings us to Section 3. This weird science has some incredibly important real-world applications, from protecting soldiers to exploring space.
This research is absolutely critical across so many fields. It's used to design safer explosives, where understanding the polymer binder's failure point can prevent an accidental detonation. It's vital for advanced body armor that's designed to stop high-speed projectiles. It helps us build spacecraft that can withstand things like micrometeoroid impacts. And it's even used in polymer foams that mitigate blast energy, protecting buildings and people.
And really, that's the bottom line. This isn't just about destruction. By studying exactly how and when these materials break down at the most fundamental level, engineers can build stronger, safer, and more resilient systems that are designed to survive the absolute worst-case scenarios.
But, the story isn't over, not even close. In fact, as much as we've learned, we've also uncovered even more that we don't know. And that brings us to our final section, the unanswered questions that are pushing the scientific frontier.
Right now, scientists are trying to create way better computer models to predict what happens in these violent, high-speed events. They're trying to figure out exactly how a polymer starting structure influences its final fate, and this is the really, really hard part. They're trying to actually watch the chemical reactions that are over and done with in just a few nanoseconds.
So how do you even solve these mysteries? I mean, imagine building a microscope that can see a chemical reaction happening during an explosion. That's pretty much what researchers are doing by developing these incredible new tools, like ultra-fast cameras and advanced spectroscopy, to get a glimpse into these fleeting, violent moments.
And that really brings us full circle. We started with a simple piece of plastic and found this hidden world of phase transitions and universal transformations. It just makes you wonder, doesn't it? What other secrets are hiding in plain sight all around us, just waiting for us to look at them under the right extreme conditions? What will we unlock next?